Welcome to today's session on the fascinating world of crystallography. In this video, we are going to break down one of the most essential concepts in crystallography, that is, symmetry in crystal and lattice structures. This includes exploring the symmetry in crystallography, crystal structure, unit cells, asymmetric unit, crystal system, Bravais lattice, and the concept of direct and reciprocal lattices. By the end of this session, you will have a clear understanding of how these concepts form the backbone of crystal structure determination. To start, let's talk about symmetry. When we think of symmetry in crystallography, we look at how crystal structure can repeat itself in space. Now, this symmetry is essential because it defines the overall shape and properties of the crystal. Symmetry describes how repeating patterns in a crystal are arranged. For example, you may have a cube where every face is identical. In contrast, a slanted, uneven shape has lower symmetry. The unique snowflakes follow symmetrical patterns formed by water molecules aligning in a crystalline structure. Symmetry in crystallography is central to understanding crystal structures. It refers to a crystal's balanced and repeating arrangement of atoms, ions, or molecules. The arrangement is not just about aesthetics, it defines the crystal's shape and plays a significant role in its physical properties, such as optical behavior, conductivity, and even stability. But how does this relate to crystals? The symmetry in crystallography helps classify crystals into different systems. But before we jump to classifying crystals, let's understand the basics of crystal structure. Crystal structure. The arrangement of atoms or ions is often visualized using a lattice. Think of the lattice as scaffolding and the unit cell as the smallest block of a skyscraper. Together, they define the whole structure. Let's break this down further. So let's start with the concept of a crystal. A crystal is a homogeneous solid where atoms, ions, or molecules are arranged in a repeating three-dimensional pattern. This regular arrangement is what gives crystal their smooth surfaces and distinct geometric shapes, including specific angles between faces. Examples of crystals include common table salt and quartz, both of which display beautiful symmetrical shapes. To understand crystals better, we introduce the idea of the crystal lattice. Think of the crystal lattice as the framework or skeleton that defines the structure of the crystal. It's an array of points extending in all three dimensions, where each point represents the position of a repeating structural unit. Essentially, it's a blueprint of where each atom, ion, or molecule should go. This lattice is what gives rise to the crystal's overall shape and symmetry. Now, within this crystal lattice, the smallest repeating segment that captures the full symmetry of the entire structure is called the unit cell. Imagine the unit cell as a small building block. If we stack this block in all directions according to the lattice pattern, we recreate the entire crystal. The unit cell's dimensions and angles determine the crystal system to which it belongs, such as tetragonal or orthorhombic. This is the foundation for categorizing crystals, as we will see when we discuss crystal systems. Within each unit cell, there is often a minimum set of atoms, ions, or molecules that can generate the entire contents of the cell when symmetry elements are applied. This minimum set is called the asymmetric unit. Here's how it works. The unit cell itself is the smallest repeating building block that defines the crystal's overall structure. However, due to crystal symmetry, such as reflections, rotations, or other symmetry operations, not all parts of the unit cell are unique. Instead, only a portion of the unit cell is unique, and the rest can be derived by applying the symmetry elements of the crystal structure. This unique portion, the asymmetric unit, is like the core blueprint. By repeating and transforming this asymmetric unit according to the crystal's symmetry operations, we can recreate the entire contents of the unit cell. In other words, the asymmetric unit is the smallest, non redundant set of atoms that, through symmetry, builds up the full structure inside the unit cell. Now that we understand the basics of the unit cell and the asymmetric unit, we can ask, how is the crystal constructed? Crystals can form in different dimensional patterns, one dimensional, two dimensional, or three dimensional, depending on how the atoms or molecules are arranged. A one dimensional crystal construction is the simplest, where atoms or molecules are aligned in a single repeating line or chain. This linear arrangement follows a single repeating pattern, forming what we can think of as a crystal along one dimension. In two dimensional crystal construction, the atoms or molecules are arranged in a repeating pattern across a flat plane. Here we see the building blocks extended in two directions, creating structures like sheets or layers that tile across a surface. Finally, in three dimensional crystal construction, which is the most common for crystals, atoms or molecules are arranged in a fully three-dimensional lattice. This creates a solid structure with a repeating pattern in all three spatial dimensions. Each of these dimensions is defined by a lattice structure, with lattice site marking points where the repeating units defined by the unit cell and asymmetric unit are placed. Whether the crystal is constructed in one dimension, two dimension, or three dimension, these lattice sites ensure that the pattern repeats consistently, giving the crystal its characteristic symmetry and structure. Essentially, it describes how the building blocks of a crystal are positioned in different spatial dimensions. Let's walk through the systematization of crystal structures, represented here as a stepwise ladder. At the foundation, we have the seven crystal systems. This system categorizes crystals based on the unit cell's geometry and symmetry properties, setting up the basic framework. The next is the 14 Bravais lattices, which combine the crystal systems with lattice centering types, like primitive and centered, to capture more structural details. Moving further, we arrive at the 32 crystal classes, defined by their point group symmetries, representing the different ways in which a crystal can be symmetrically arranged. Finally, at the top, we have the 230 space groups. This is the most complete level of symmetry, encompassing all possible spatial symmetries in crystals, including translations, rotations, and reflections. This hierarchical structure provides a systematic approach to understanding and categorizing crystal structures, from basic metrics to complete spatial symmetries. For the scope of this video, we will focus on the first two foundational steps in the systematization of crystal structures: crystal systems and Bravais lattices. So first, let's dive deeper into 7 crystal systems. Starting with crystal systems defined based on the geometric parameters and symmetry of the unit cell, specifically looking at the length of the cell edges and the angles between them, which form the basic structural framework for classifying crystals. Let's walk through each one of them. So first is cubic. This is the most symmetric system. In cubic crystals, all sides are equal and all angles are exactly 90 degrees. Think of a perfect cube where each edge and angle is identical. This high symmetry is characteristic of many naturally occurring minerals. Tetragonal. In the tetragonal system, two sides are equal, but the third is different. All angles remain 90 degrees. So imagine stretching a cube along one axis. This gives us a shape that's longer in one direction but still maintains symmetry in the other two. Orthorhombic. Here, all sides are unequal, but like the previous systems, all angles are still 90 degrees. The orthorhombic system looks like a stretched or squished box, maintaining right angles but with no equal edge lengths. Monoclinic. In the monoclinic system, all sides are unequal, with two angles at 90 degrees, but one angle is different. This slight asymmetry creates a structure that's skewed along one axis. Hexagonal. The hexagonal symmetry is unique with its four axes. Three of these axes are equal in length and intersect each other at 120-degree angle, while the fourth axis is perpendicular to the other. This arrangement gives hexagonal crystals their distinctive six-sided shapes, like quartz. Trigonal or rhombohedral. Now, this system is similar to the cubic but slightly distorted. None of the angles are exactly 90 degrees. Imagine a cube tilted along its axis so that its angles are no longer right angles, creating a rhombohedral shape. Lastly, triclinic. So finally, the triclinic system has the least symmetry. In this system, none of the sides are equal and none of the angles are 90 degrees. This irregularity makes triclinic crystals the least constrained in terms of symmetry, giving them a unique and highly asymmetrical shape. Each of these crystal systems provides a foundational way to categorize crystals based on their geometry and symmetry. By understanding these categories, we get a glimpse into the beautiful diversity of crystal structures found in nature. Now that we have covered the 7 crystal systems, which classify crystals based on their unit cell shapes and angles, let's dive deeper into the idea of lattice arrangement with the 14 Bravais lattices. So, what are Bravais lattices? The Bravais lattices take the crystal systems we just discussed and explore how lattice points, which mark the positions of atoms, ions, or molecules, can be arranged in three-dimensional space. There are precisely 14 unique ways to arrange these points, and we can call these the 14 Bravais lattices. Each arrangement follows the symmetry of one of the seven crystal systems, but adds unique configurations to accommodate different types of structural layouts. These 14 Bravais lattices are classified based on how the lattice points are positioned within the unit cell. There are four main types. First is primitive. In primitive lattices, lattice points are found only at the corners of the unit cell. This is the simplest arrangement and forms the base of many crystal structures. Second is body centered. Body centered lattices have lattice points at the corners and an additional point right in the center of the unit cell. This arrangement adds internal symmetry and stability to the structure. Third is face centered. In face centered lattices, we find lattice points at each corner and at the center of each face of the unit cell. This setup maximizes the lattice points within the structure, creating a densely packed arrangement. And lastly, base centered. Finally, in base centered lattices, there are lattice points at each corner and also at the centers of two opposite faces. This type of arrangement is often seen in crystals with layered structures, where alternating layers add unique properties to the crystal. By combining the seven crystal systems with these four types of lattice point arrangements, we arrive at the 14 Bravais lattices. Each lattice provides a unique way of organizing atoms, ions, or molecules in space, leading to the diversity of crystal structures. Understanding the Bravais lattices helps us connect the fundamental shapes of the crystals with their more complex real world arrangements. With an understanding of the 14 Bravais lattices, which show us how lattice points can be arranged in space, we are ready to explore a new layer of crystal structure analysis: direct and reciprocal lattices, a more abstract but essential concept, especially when we are using X-ray diffraction to study crystals. Direct and reciprocal lattices. The direct lattice is the familiar lattice we have been discussing, where atoms, ions, or molecules are positioned in real space. However, to understand certain properties of crystals, like diffraction patterns, we also use the reciprocal lattice. The reciprocal lattice is a mathematical construct that represents the spatial frequencies of the direct lattice, providing insights into wave interactions with the crystal structure. Now, let's take a closer look at how we construct the reciprocal lattice from the real lattice. In real space lattice, we define directions using lattice vectors A, B, and C and their respective angles alpha, beta, and gamma. Each vector represents a direction along which atoms or molecules are periodically arranged within the crystal. To create the reciprocal lattice, we generate a new set of lattice vectors, denoted with an asterisk. These vectors are perpendicular to the corresponding planes in the real lattice and are inversely proportional to the real lattice distances. In essence, each point in reciprocal space corresponds to a plane in real space, and the spacing between these points relates to the interplanar spacing of these planes in the crystal. By knowing the relationships between real and reciprocal vectors, we can interpret diffraction patterns and derive information about the crystal's internal structures. Just as we have a unit cell in the Dirac lattice that defines the repeating structure, we have a reciprocal unit cell in the reciprocal lattice. The dimensions and angles of the reciprocal unit cell are derived from those of the real unit cell, but they reflect the spatial frequencies rather than actual physical distances. So let's take a closer look at their relationship. In the real unit cell, as shown here, we define the basic repeating structure in the crystal's Dirac lattice, where atoms, ions, or molecules are physically arranged, whereas the reciprocal unit cell is derived from this real unit cell by mathematically transforming its dimensions, creating a space that represents the crystal's spatial frequencies rather than actual distances. One key concept to note is the inverse relationship between these two cells. If the real unit cell becomes larger, the reciprocal unit cell becomes smaller, and vice versa. This inverse relationship is fundamental in crystallography because it allows us to use reciprocal space to analyze how waves, like X rays, interact with the crystal structure. For example, in X ray diffraction, the patterns we observe are actually reflections of the reciprocal lattice, making this concept indispensable for studying crystal properties. To wrap up, we started by understanding the building blocks of crystal structure and symmetry in crystallography, moving through crystal systems and Bravais lattices. Each of these concepts is interconnected, helping scientists decipher the arrangement of atoms in crystals. We then explored the concept of direct and reciprocal lattices, which allow us to interpret both the physical arrangement and spatial frequencies within a crystal. The reciprocal lattice and its unit cell give us powerful tools for analyzing crystal properties, especially in the context of diffraction and other wave based phenomena. Thanks for listening, and I hope this video has provided a clearer picture of how symmetry governs crystal structures and lattices. Feel free to check out the supplemental handout for image resources and references.